Thermal equilibrium is a steady state condition at a given temperature without any external excitations such as light, pressure, and electric field. Let us understand this statement with an example. Let me take a crystal silicon as example, which can be represented in band model as shown here and bond model here at a temperature of assumption 0 Kelvin. At 0 Kelvin, all the bonds are intact where the electrons are in the bonds, and similarly in band model where the electrons are all in valence band and completely the conduction band is empty. Let us see if we increase the temperature from 0 Kelvin to some T equals to T1 Kelvin, where T1 is greater than 0 Kelvin. And we are assuming we will keep this T1 constant without changing. Now, as the temperature increased from this case to this case, the silicon atoms in the crystal will start vibrating. And this vibration of silicon atoms in the crystal is called phonons. Because of these vibrations, these bonds can potentially break, which will give rise to a free electron, leaving a hole here. Similarly, in band model, we can see this one of the electron in valence band will acquire enough energy because of the thermal excitation, the presence of temperature, to conduction band, which means we'll have an electron in the conduction band. Because it came to conduction band, we'll have an empty state which is called hole in the valence band. If you are looking only in conduction band, because of this thermal excitation, a new electron pops up in the conduction band as if it is generated out of nowhere. But if you see here, this electron came from valence band. So we call this process as generation, and this generation is because of the thermal excitation. So we call this thermal generation of electron and hole. So we call this process as electron hole pair generation because of thermal excitation. In short form, we call this electron hole pairs as EHPs. Now, to summarize, we have this atoms vibrating, we call it phonons. As they vibrate, they can cause bonds to break, which will give rise to electron hole pairs generation. Because of this thermal generation of electron hole pairs, the number of electrons in conduction band will keep on increasing, and the number of holes in the valence band will keep on increasing. But now, a simple question to ask, will this electron concentration in conduction band and hole concentration in valence band will keep on increasing monotonously? Definitely not, because then you wouldn't have any electrons in the valence band. They will all be turning up in conduction band. It doesn't seem to be intuitive, and it doesn't seem to be even steady state or sustainable state. Because of these carrier concentrations N and P increasing, there will be another phenomenon that will get triggered, which we are going to call as the recombination, because we have more electrons in conduction band now, because of which electron would actually now recombine with an existing hole in the valence band. This we call recombination. Now let us call this generation rate, the number of carriers generated per centimeter cube per unit time, is GTH, representing the thermal generation rate. Now the recombination rate, as well as, let's call it RTH, the recombination rate. Now the question is, should they be different or equal? If they are different by any chance, let's say GTH is greater than RTH, then the number of carriers in conduction band would still keep increasing, which is again not a sustainable condition. So a conclusion from this one is the generation rate in steady state should be equal to the recombination rate, so that the number of carriers in the conduction band would remain constant with respect to time. So we can write in steady state the GTH should be equal to RTH. Of course, if you see, because there was a brief time of transient in which, because the temperature changed, initially the generation rate was present, no recombination rate. As the carriers in the conduction band increase, it gives rise to a recombination rate as time progresses. And then for a moment, we'll have generation rate greater than the recombination rate. But when we reach to a steady state, the generation rate and recombination rate should be equal. Now by that time, because for a brief moment we had some generation greater than recombination, the carrier concentration would be finite in steady state, which was 0 in the previous state where T was 0 Kelvin. When it was T equal to 0 Kelvin in steady state, we had this condition on the left side. And when we increase the temperature, for a brief moment, what happened is the atoms started vibrating and bonds were breaking. It gave rise to electron hole pair generation. We called it thermal excitation. And then because the carrier concentration increased, it triggers a reverse phenomenon called the recombination, because of which the carrier concentration in the conduction band would not increase further. It will remain constant with respect to time, assuming the temperature is fixed. A point to note, generation can be caused because of various phenomena like incidence of light, pressure, and applying of electric field as well. So that's why we assumed in defining the thermal equilibrium that there are no external excitations whatsoever except the temperature itself. That's why we call this a thermal equilibrium. Now you see, this is actually a steady state at which the carrier concentrations in conduction band and carrier concentrations in valence band will be fixed. It doesn't change, even though there is a generation rate and recombination rate, which means constantly carriers are excited and constantly they're recombined. But as such, with respect to time, carrier concentrations doesn't change. So this is thermal equilibrium. Even though we took an example of intrinsic semiconductor here, but it doesn't really matter because thermal equilibrium is a very generic phenomenon that is true even in other semiconductors like the extrinsic semiconductors. We have talked about only generation and recombination so far, but in general there will be a lot of processes that will be happening inside the semiconductor. So in generic, we can say that for every process there will be an anti-process which will balance it exactly in thermal equilibrium. And of course, it is a steady state where temperature is fixed and no external excitation at all.